You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Retrieval evaluation begins with a deceptively simple idea. How do we know if a system is returning the right information? For a user, this boils down to whether their question is answered quickly and clearly. But for system designers, that intuition must be translated into measurable terms. Without evaluation, we cannot compare one system to another, nor can we tell if a new model or indexing method is an improvement or a regression. Imagine running a library without any feedback on whether the catalog helps readers find what they need. The librarians might keep rearranging books, adding new categories, or renaming things. But without evaluation, they would have no evidence that these changes helped. Retrieval evaluation is essentially the feedback loop that prevents chaos. It gives designers and engineers a systematic way to test whether the system is fulfilling its purpose, connecting questions with the information that best satisfies them. The role of evaluation in modern information systems is much larger than most users realize. Search engines, enterprise knowledge bases, and retrieval-augmented generation systems now sit at the center of decision-making in nearly every domain. A doctor querying medical guidelines, a lawyer researching precedent, or a compliance officer scanning regulations all rely on systems to be accurate, comprehensive, and timely. If these systems slip, the consequences ripple outward into real-world decisions that may affect health, finances, or safety. Evaluation serves as the guardrail that ensures scaling does not mean drifting away from accuracy. When billions of queries are processed daily, even small inefficiencies or biases can magnify into widespread user frustration. Evaluation is therefore not a technical afterthought but an operational necessity. It keeps systems honest by verifying that they deliver on their promises, regardless of size or complexity. At the center of retrieval evaluation lies the concept of ground truth. Ground truth is the reference set of judgments used to define what is relevant for a given query. For some domains, this might be created by experts, such as doctors labeling which studies answer a clinical question, or legal professionals marking which cases apply to a statute. In other contexts, ground truth may be inferred indirectly from user behavior, such as click patterns or how long a person dwells on a page. The reliability of evaluation depends entirely on the reliability of this ground truth. If the labels are biased or incomplete, the metrics will reflect those flaws, creating a distorted view of system quality. Think of ground truth as the grading key for an exam. If the key itself contains errors, even the best answers will look wrong. Establishing high-quality ground truth is therefore one of the hardest but most crucial parts of retrieval evaluation. Recall is one of the simplest metrics, but it reveals something essential about retrieval: completeness. Recall measures the proportion of relevant items successfully retrieved by the system. In practice, this means asking, did the system capture everything that mattered? If there are 100 relevant documents and the system surfaces 90, recall is 90%. This matters enormously in domains like e-discovery or compliance, where missing even a single item could have serious consequences. Imagine a company investigating whether it complied with environmental regulations. If the retrieval system overlooks one key regulatory update, the company could face penalties, despite believing it had done due diligence. High recall is critical in such context because users need to be confident they have seen the full picture. However, recall alone does not guarantee usefulness, since a system might achieve high recall by returning a flood of irrelevant material. Precision provides the counterweight to recall by measuring how much of what was retrieved is actually relevant. If a system retrieves 100 items but only 40 are useful, the precision is 40%. High-precision systems are prized in user-facing contexts where overwhelming people with noise leads to frustration. For example, if an employee searches an internal knowledge base for remote work policy, they expect the first page of results to contain only the relevant documents, not dozens of loosely related memos. Precision captures this sense of quality, fewer but better. Yet optimizing for precision often reduces recall, since tightening filters may exclude some relevant items. The interplay between recall and precision reflects a fundamental trade-off. Do we want to ensure nothing is missed, or do we want to ensure that what is shown is consistently useful? The balance depends on the stakes of the task and the patience of the user. Recall at K adds an important layer by acknowledging that relevance hidden at the bottom of a long result list may as well be invisible. Most users do not look past the first page of results, and many only consider the first handful. Recall at K measures whether relevant items are included within the top K results, where K might be 5, 10, or 20. For example, if a legal researcher needs case law on a specific issue and the relevant ruling appears as the 30th result, the system technically, quote, found it, but the researcher is unlikely to benefit. Recall at K translates recall into a measure of practical usefulness. Did the system surface the relevant material quickly enough for users to notice? This metric is especially important for time-sensitive applications, like question answering in chat systems, where users expect an answer almost instantly. It forces retrieval pipelines not just to capture information but to prioritize it effectively. Mean reciprocal rank, or MRR, makes this user-centered perspective even sharper. Rather than asking whether relevant material is present at all, MRR looks at how soon the first relevant result appears. If a system consistently places the correct answer in the first position, MRR scores approach perfection. If it often pushes relevance further down, the score falls accordingly. MRR aligns closely with human behavior, since most people stop searching once they find a satisfactory answer. Consider a customer service portal. If the top suggestion solves the problem, the user is satisfied. If they must scroll through irrelevant entries before finding the right one, frustration grows. MRR quantifies this experience, turning "how soon do I get what I need" into a measurable property of the system. It is particularly suited to domains where one good answer is enough to resolve the query. Normalized discounted cumulative gain, or NDCG, offers a more nuanced view by recognizing that not all results are equally relevant and that their order matters. Instead of treating relevance as binary, NDCG allows for graded judgments. A result may be highly relevant, somewhat relevant, or marginally relevant. Moreover, it discounts relevance based on rank, reflecting the reality that users value early results more highly. This captures the complexity of real-world relevance. Imagine a user searching for treatments for type 2 diabetes. The top result might be a guideline from a health authority, highly relevant, while another might be a patient blog, somewhat relevant. NDCG rewards systems that surface the authoritative source first, while still giving partial credit for including the blog further down. This metric mirrors the subtlety of human judgment, making it especially important in consumer-facing search and recommendation systems where ranking quality directly affects satisfaction. The diversity of metrics reflects different philosophies about what matters in retrieval. Recall emphasizes completeness, ensuring that nothing relevant is overlooked. Precision emphasizes quality, ensuring that what is shown is consistently useful. MRR emphasizes speed of success, rewarding systems that help users quickly find their first good answer. NDCG emphasizes ranking quality, rewarding systems that order results intelligently based on graded relevance. These differences reveal why no single metric suffices for evaluation. Choosing which metric to prioritize is not just a technical decision, but a reflection of the system's purpose and its users' needs. A system serving compliance officers may live or die by recall, while one serving online shoppers may hinge on NDCG. Evaluation is therefore not about chasing numbers blindly, but about making explicit choices about what success means in a given context. User-centric evaluation reinforces this point by anchoring metrics to the actual goals of real people. Users are not abstract entities following equations. They have tasks, expectations, and limits. A system might achieve a high recall score but still leave users dissatisfied if relevant answers are buried, or if irrelevant noise dominates the top ranks. Conversely, a system with modest recall might delight users if it consistently provides quick, useful answers to common questions. Evaluators must remember that the ultimate judge is not the metric but the user's experience. This is why modern evaluation often incorporates behavioral data such as clicks, dwell time, or survey responses. Metrics guide us, but user experience validates whether the system is succeeding in practice. Task-specific evaluation acknowledges that different retrieval tasks require different definitions of success. In some cases, like fact retrieval, users only need one good answer. Here, MRR or recall at the first of may be the most informative metric. In recommendation systems, diversity may matter as much as precision, since users value being exposed to varied options. In compliance or e-discovery, recall dominates because missing even a single item could carry legal consequences. Evaluation must therefore be tailored, not generic. It is dangerous to apply the same metric across all tasks because what counts as success varies dramatically by context. Task-specific frameworks remind us that evaluation is a tool for shaping systems to their purpose, not a one-size-fits-all solution. Offline metrics provide structure, but they also have clear limitations. They rely on fixed datasets with labeled judgments, which do not always capture dynamic user needs or evolving contexts. A retrieval system might perform well on a benchmark created last year, yet fail to satisfy users today if the information landscape has shifted. For example, during a breaking news event, articles judged relevant a week ago may no longer meet user expectations for freshness. Offline metrics are therefore best viewed as baselines. They provide stability for comparison, but they cannot fully capture live user satisfaction. They must be complemented by online evaluation methods to create a complete picture of system quality. Standard benchmarks have become essential for comparing retrieval systems across research and industry. MS Marco, with its large set of real-world web queries and human-labeled passages, has driven progress in neural retrieval methods. BEIR, which offers a suite of tasks across diverse domains, tests how well systems generalize beyond narrow training sets. Benchmarks provide common ground for progress, ensuring that innovations are not anecdotal but measurable. However, they can also narrow vision, encouraging researchers to optimize for specific datasets at the expense of real-world generality. Benchmarks are powerful, but they are only part of evaluation, not the whole story. They serve as laboratories where systems can be tested, but true performance must also be validated in the wild. Bias in ground truth data adds another layer of difficulty. Annotators may unconsciously favor certain perspectives, and click-based judgments reflect what is popular rather than what is most authoritative. For example, in a political context, annotators' biases may shape what is judged as relevant, while user clicks may reinforce mainstream sources over minority voices. These biases seep into metrics, skewing evaluations and shaping the systems themselves. Awareness of bias is therefore essential. Evaluators must diversify annotator pools, scrutinize labeling guidelines, and treat ground truth not as absolute but as approximate. Only then can metrics like recall, MRR, or NDCG be interpreted responsibly. Interpreting recall requires thinking about it not as a mathematical fraction but as a measure of how quickly a system surfaces relevant content to the user. Imagine a student preparing for an exam who types "causes of the French Revolution" into a search tool. If the top 10 results contain at least one clear and relevant explanation, recall at 1-0 is satisfied. If the first relevant content only appears at rank 50, recall at 1-0 fails, even though recall overall might look good because the system eventually finds relevant material. This metric is practical because it reflects human patience. Very few people browse beyond the first page or two of results. Recall is therefore a diagnostic about user experience. A retrieval pipeline that scores high on recall demonstrates that it does not just capture relevance somewhere in its results, but brings it forward into the range users are actually likely to see and use. Mean reciprocal rank, or MRR, offers a different lens by highlighting how efficiently a system gets a user to their first useful answer. Consider a support portal where employees ask about vacation policies. If the correct document consistently appears in the first slot, the reciprocal rank is 1, and averaged across queries, the MRR will be high. If answers often appear in the 5th or 10th slot, the MRR falls, signaling inefficiency. This metric is especially valuable in contexts where a single good result suffices to meet the user's needs, such as troubleshooting guides or fact-finding tasks. It embodies the user's perspective of satisfaction. How soon do I find something useful? While recall speaks to completeness and precision to quality, MRR captures speed of success. Systems optimized for MRR feel quick and helpful, even if they do not always capture every possible relevant result. Normalized discounted cumulative gain, or NDCG, introduces nuance by rewarding systems not only for including relevant results, but also for ranking them intelligently. Imagine searching for symptoms of Lyme disease. A government health authority's article is highly relevant, while a general health blog is somewhat relevant. If the official source appears first and the blog later, NDCG rewards this ordering because users see the best material early. If the reverse occurs, the score drops, even though both items are technically relevant. This metric reflects the layered nature of real-world relevance, where some answers are authoritative and others are marginal. By discounting relevance as results fall lower in rank, NDCG mirrors how people actually scan search results, paying most attention to the top. In systems where ordering is critical, such as e-commerce or recommendations, NDCG is especially valuable. It tells designers not just whether relevance is present, but whether it is prioritized properly. Composite metrics arise from the recognition that no single measure captures all aspects of retrieval quality. A system might excel in recall but perform poorly in precision, or it might rank one good answer high but miss others entirely. To balance these competing dimensions, composite metrics combine multiple signals, often weighting them differently depending on context. For example, a medical search system might combine recall and NDCG, ensuring both completeness and ordering of results. An enterprise knowledge base might emphasize MRR alongside precision, prioritizing quick answers without clutter. These combinations reflect pragmatic decision-making. Evaluation is not about maximizing abstract formulas, but aligning system performance with user goals. Composite metrics therefore serve as customizable dashboards, letting organizations define what success looks like in their domain and measure it accordingly, rather than being locked into a one-size-fits-all view of relevance. Offline metrics provide consistency and stability, but online evaluation methods capture how systems perform in the wild. A/B testing, for instance, compares two versions of a retrieval system by exposing different groups of users to each and measuring satisfaction or task completion. Interleaving techniques blend results from competing systems into a single ranked list and observe which set users prefer. These live methods reveal how evaluation metrics translate into behavior. A system that looks strong on recall at the 10th of may still disappoint users if it surfaces too much irrelevant noise at the top. Online evaluation complements offline scores by grounding them in human experience. It is especially important for systems that evolve continuously, such as web search engines, where user behavior provides constant feedback loops. Offline metrics remain valuable, but online methods close the gap between laboratory benchmarks and lived user experience. Implicit user signals expand evaluation beyond annotated ground truth. Click-through rates, dwell time, scrolling behavior, and even abandonment can all indicate whether a result satisfied the user. These signals are not perfect. Users may click on irrelevant items out of curiosity or avoid relevant items because they already know the answer. Yet, when aggregated at scale, implicit signals provide rich insights into retrieval quality. Consider a recommendation system. If users consistently engage with items near the top of the list, it suggests the system is ranking effectively. If engagement drops off despite high offline scores, there may be a mismatch between metrics and user expectations. Incorporating implicit signals ensures evaluation reflects not only labeled relevance, but also how people actually interact with results, making the system more responsive to real-world needs. Evaluation also plays a critical role in detecting drift, whether in data, content, or user behavior. Over time, the information landscape changes, new regulations appear, terminology evolves, or user interests shift. A retrieval system that was finely tuned 6 months ago may begin surfacing outdated or irrelevant material today. Continuous evaluation highlights these shifts by tracking how performance metrics degrade over time. For instance, falling recall at the 10th of May signal that new content is being missed in indexing pipelines. Decreasing NDCG might reveal that ranking models are failing to prioritize newer, more authoritative sources. By integrating evaluation into ongoing monitoring, organizations can detect drift early and adjust pipelines before user trust erodes. Evaluation thus becomes not just a measure of current performance but a safeguard for long-term system reliability. Latency is another dimension that evaluation must account for, even though it is not a measure of relevance. A retrieval system that produces perfect rankings but takes 5 seconds to respond may still fail in practice. Users expect speed as well as accuracy. Evaluation frameworks increasingly incorporate latency as part of system quality, measuring how quickly relevant results are delivered. This is especially critical in conversational AI, where delays break the flow of dialogue. Balancing accuracy and latency is a core design challenge, and evaluation ensures neither is ignored. A system with high recall but poor response time is impractical. Conversely, a lightning-fast system that misses key results undermines trust. Including latency in evaluation reflects the holistic reality of user expectations. Answers must be both good and timely to be effective. Scalability of evaluation becomes a pressing issue in large systems where content and queries number in the billions. Manual annotation of relevance is impossible at this scale, and even offline metrics can be expensive to compute on massive datasets. Automation becomes essential. Sampling techniques allow evaluation on subsets that statistically represent the whole. Machine learning models trained on annotated data can extend judgments to unlabeled queries, approximating ground truth. Automated pipelines track metrics continuously, flagging anomalies without human intervention. These approaches ensure that evaluation keeps pace with system growth. Without scalable evaluation, organizations risk blind spots, where only small slices of the system are measured while most of it operates unchecked. Scalability ensures that evaluation remains a living process, not a static report card. Security and compliance must also be considered in evaluation frameworks. A retrieval system can perform well on recall and precision, yet fail catastrophically if it surfaces sensitive or restricted data to the wrong audience. Evaluation must therefore include tests for whether access controls are respected and whether compliance boundaries are maintained. For example, in a healthcare system, evaluation might check that patient records are never retrieved outside authorized contexts. In legal environments, evaluation may verify that privileged documents are excluded from general search. Security is not traditionally thought of as part of retrieval evaluation, but in high-stakes domains it is inseparable. A system that leaks confidential data is, by definition, a failure, no matter how well it scores on NDCG. Multilingual retrieval introduces unique evaluation challenges. A system that performs well in English may falter when queries are issued in Spanish, Arabic, or Hindi. Evaluation must therefore extend across languages, ensuring that metrics capture cross-lingual relevance. This often involves creating multilingual benchmarks, where queries in one language are judged against documents in another. For example, a user searching in French may expect documents originally written in English to surface. Evaluation frameworks must measure whether systems bridge these gaps effectively. Without multilingual evaluation, retrieval systems risk becoming biased toward dominant languages, undermining inclusivity. As global systems increasingly serve diverse audiences, multilingual evaluation is becoming a core requirement, not an optional add-on. Domain-specific evaluation tailors metrics and benchmarks to specialized contexts like medicine, law, or finance. In medicine, for example, relevance may be judged not only by topicality but also by clinical reliability and evidence strength. In law, relevance may hinge on jurisdiction or precedential value. Generic benchmarks cannot capture these nuances. Domain-specific evaluation therefore designs custom datasets, labels, and metrics that reflect professional standards. This ensures retrieval systems are judged not by abstract notions of relevance, but by criteria that matter to practitioners. Without domain-specific evaluation, systems may look strong on general metrics while failing in their intended use cases. Tailoring evaluation keeps retrieval accountable to the people who depend on it most. Continuous improvement loops depend on evaluation as their engine. Retrieval systems are never static. They evolve through new data, algorithms, and user behavior. Evaluation provides the feedback that guides this evolution, identifying weaknesses, measuring improvements, and validating changes. For example, if evaluation shows that recall at 1.0 is dropping, engineers know to adjust indexing. If NDCG improves after a new re-ranker, they can justify rolling it into production. This loop ensures systems do not drift aimlessly, but improve iteratively in response to evidence. Continuous evaluation transforms retrieval from a static artifact into a dynamic, living system that adapts to changing needs. Looking ahead, new approaches are emerging to enhance retrieval evaluation. One promising trend is the use of large language models themselves as evaluators. These models can read query result pairs and provide judgments of relevance, reducing reliance on costly human annotation. While imperfect, they offer scalability and flexibility, especially in domains where labeled data is scarce. Another trend is adaptive evaluation, where metrics adjust dynamically based on query type or user intent, ensuring that systems are measured in context rather than against generic standards. These innovations reflect the growing recognition that evaluation must evolve alongside retrieval itself. The goal is not just to score systems but to understand them deeply, guiding their design and ensuring they continue to meet human needs in an ever-changing information landscape. Finally, retrieval evaluation connects directly to grounded generation, the subject of the next episode. Large language models increasingly depend on retrieval pipelines to supply relevant context before generating answers. If retrieval is weak, generation will falter, producing hallucinations or irrelevant text. Evaluation ensures that retrieval delivers the right building blocks for generation, providing a foundation of trust. Metrics like recall at K, MRR, and NDCG thus play a role not only in search engines but in shaping the quality of generative AI itself. By testing retrieval rigorously, evaluation protects the integrity of systems that rely on it downstream, ensuring that the answers users receive are both relevant and grounded. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.